won't be presented by me, but I will present Dmitry Karpinsky. So welcome. Dmitry is a graduate from the Vitebsk State University in 2001. And since that time, he has had about 20 years of teaching and research experience. 8 of those were actually here in Avail. So welcome back. I'm sorry it's only a welcome back virtually, obviously, but welcome back all the same. He is now the head of the laboratory in the Scientific Practical Materials Research Center of the NAS in Minsk. And his work interests are in magnetic transport properties, solids, piezoelectricity, and polarization phenomena. And today he will give us a lecture on XRD, X-ray diffraction. So a big welcome to Dmitry, and please, if you can share your talk now.
Okay, thank you, Duncan, for presenting me. It was really nice time being in Avail. I spent several years there, and it was a real pleasure. So I'm really glad to see all of you, my colleagues, friends here, and it's an honor to be the first speaker to present my talk. So let's go to the presentation. Sorry for possible technical problems. So let's start how it works. Okay, probably it works like this and this. Can you see the slide, the first one?
Yes.
Okay. Nice. I don't know about this, how it looks from your side, because I see only my screen, full screen mode. So I will talk about diffraction techniques, and we will talk about, and you will ask probably some questions. Talk about what kind of radiation we can use, X-ray or Synchrotron radiation, or neutron diffraction. So what we will speak about X-ray radiation, synchrotron radiation, and radiation sources, how to produce. We will also talk about neutrons, because it's a very powerful technique, neutron diffraction. We will talk also about this. About scattering and diffraction techniques and the possible experiments. Some words about crystal structure and the Rietveld method, which is a very powerful method to refine the crystal structure of material. A few phrases about the software we can use to. Okay, let me check if everything is okay with the connection, because I don't see any. It's okay, yes?
Yeah, everything's fine.
Okay, nice. Because
Professor Dmitry, we are looking now. It's okay. Right now.
Okay. So, and then I will talk about the refinement for particular material, some cobaltite, to show how it works. I mean, software, which we can use to refine the crystal structure. So let's go to the X-ray or to electromagnetic radiation. So you know that X-ray radiation is a type of electromagnetic radiation, and it's packed into photons, so-called quantums of electromagnetic radiation. And photons, they don't have a mass, and they have a constant speed in the given medium. For vacuum, it's the speed of light. How to produce electromagnetic radiation, in contrast to particle radiation like neutrons or alpha particles. Okay, how to produce it? We know that charged particle, which is accelerated, it emits electromagnetic radiation. And as an example, we can show usual antenna, and the AC current generate electromagnetic waves. Looking on the energy bar, we can say that we can divide, depending on the energy of the radiation, we can divide and distinguish radio waves, microwaves, infrared, our visible spectrum, which is quite narrow stripe on this energy bar, ultraviolet, X-ray, gamma, and cosmic rays. So depending on the energy region, it's more convenient to say, to describe electromagnetic radiation by wavelengths. Like for radio waves, we speak about frequency, usually, yeah, like radio megahertz region, yeah. For microwaves, we usually say about wavelengths, centimeters. For visible spectrum, it's also wavelengths. The range is present on the slide. And for gamma X-ray, we can also use wavelengths in angstroms, say, for X-ray, for conventional X-rays in the lab, or energy in electron volts, kilo electron volts. So, how these X-rays were discovered? They were discovered by German physicist Wilhelm Röntgen a long time ago, and for his discovery, he got the first Nobel Prize in the history. It was quite interesting personal story, how he was expelled from the technical school, and by the way, without certificate, he was able to become a student of Federal Polytechnic Institute in Zurich. Now it's ETH. Probably our colleague Mark can explain how it was. Is it really possible to become a student without certificate? But it was possible at that time, or at least for Röntgen. So, and then there is a list of universities where he was working, and in the University of Würzburg, in 1825, he discovered in his lab, and we have a photo, he discovered this X-ray, I guess everyone knows why X, because it's something new. He discovered this type of radiation. The lab is not, looking at the photo, the lab is not really well equipped, but it was enough for Röntgen to make one of the brilliant discovery in that century. So, how to produce X-rays, and now the method is more or less the same like that which Röntgen used long time ago. So we have the X-ray tube, which is an electric vacuum device. The main parts are cathode and anode electrodes, and the filament which produce electrons because of thermal activation. So the filament is heated, and the electric field accelerates these electrons, which collide with the material of anode and produce X-rays, so electromagnetic radiation in this particular energy range. We have to note that main part of this emission is so-called breaking radiation, or German term Bremsstrahlung, probably because it was discovered by German physicists. And only 1% of this radiation, of this emission, really important on the useful for our experiments for diffraction. So this useful part of the radiation called characteristic because it's characterize the material of anode because of the transfer from L to K layer of the electron orbits, and this action produced the characteristic radiation. And on the spectrum, you can see that for breaking radiation, the spectrum is solid, and for characteristic radiation, we have some discrete, very narrow and high intense lines. So this is X-ray, how we can produce it in the lab. But also we can produce X-rays in synchrotron. The first time people have observed some glowing in the synchrotron quite a long time ago, 1947, the first synchrotron, and this emission was considered, and it's really the fact, it's considered as parasitic effect. So the electrons were accelerated in the synchrotron, and they start to emit X-rays, and it means they lose energy. So that's a problem, and we have to increase power to keep the electrons on the orbits or trajectory. So this parasitic effect, it's really important for some experiments like X-rays. And how this emission happens in the synchrotron. So we already know that the charged particle, like electron, emits radiation, and usually the shape of this emission is like torus. But then the speed of particle increase up to the speed of light, or become to be relativistic. This front drastically change its shape, and the closer we are to the speed of light, this front becomes more symmetric. Say for beta, beta is a ratio between the speed of the particle and the speed of light. This front becomes to be more symmetric, more and more and more. So, and the power of this radiation also change. This is the formula for power of emission for non-relativistic and relativistic case. So this is really important method to produce X-rays. In reality, how it looks, the synchrotron. So we have the GAN of electrons, or linear accelerator. We have a booster ring where we accumulate the electrons, and the so-called storage ring, the big one. In the storage ring, to keep the electrons on the trajectory, we use bending magnets, yeah, because of interaction between magnetic field and the charged particle. We can keep them inside this guideline. So this is the scheme, and usually it's enough, okay. But for scientists, never the energy and the brilliance, so-called the parameter of radiation is not enough. So then people discovered so-called insertion devices. Insertion devices, this is special devices which are installed inside these guidelines, and at least we will consider briefly two types of these insertion devices, wiggler and undulator. So what happens there? Then the electron trapped or comes into this device, it will change its trajectory, because what is the wiggler? It's just a set of permanent magnets with oppositely aligned poles. And depending on the geometry, how they are arranged in the space and in these magnets, we can say about wiggler or undulator. Wiggler gives solid spectrum of emission, and undulator, because of interference, gives us discrete spectrum. So in reality, wiggler, probably I can show the pointer. Probably. Okay, you have on the slide, you see the photo of the undulator, and on the next image, you can estimate the geometry of this undulator and the guy who is trying to understand how it works, it's me. It was made in Desi, German Synchrotron Center. Oh, I see some marks. I don't know. Probably later we can I can answer some questions. So okay, again about the radiation in synchrotron. Without insertion devices, just having bending magnet, we have solid spectrum. With Wiggler, we have also solid, but with a higher intensity of the emission. And with undulator, we have some discrete peaks, and this is more intense radiation we can get in the synchrotron. So around the storage ring, usually we, or the organizers, locate different experimental stations, so-called, and between the storage ring and the experimental station, we have a guideline, and inside this guideline we have some so-called optic, which can cut the proper energy range from the radiation, depending on the purpose of the experimental station. So okay, and a few words about the parameters. What are the main parameters of the synchrotron radiation? It's the brightness. So it's defined as a power per square per angle, or spectral brightness. Also, we consider the bandwidth. This is most important characteristic, and you can find these parameters on the center you would like to apply for your experiments. So this is just briefly to explain the overall picture. And about the synchrotrons which are now in operation in the world, now we are somewhere between third and fourth generation. Main centers can be ascribed to third generations. It's a generation, we can say, okay, how to produce X-ray emission. Yeah, if on the first step we can use, or we used only laboratory facilities, now we can use synchrotrons, and the next step is so-called free electron lasers. And if I remember well, the scientific center now start to operate in, which use this principle, free electron laser, in Sweden. And this is really sophisticated center. Okay, this is just about the synchrotron facilities. And on the map, you can see that there are actually a lot of centers around the world. Not all are marked on the map, but still they have something to choose. A lot in United States, and more powerful in United States, the sources of synchrotron radiation. But in Europe, we also have some nice centers, and one of the most important, I would say, with the highest brilliance among the European center, it's European Synchrotron Research Facilities at Grenoble in France. And you can see the photo of this storage ring. Yeah, I was talking about the storage ring, and now we can see how it looks in reality. The diameter is more than 100 meters, so it's a really big building. And on the scheme, you can see how many instruments they are marked by these abbreviations. The instrument which are located around the storage ring. And each instrument is focused on some specific type of experiment. So, but I'd like to be focused on the diffraction. So let's talk about diffraction. But among the, or not among the experiments, depending on the type of this type of interaction, we can make different types of experiments. Say small angle X-ray scattering. But again, the topic of my talk is diffraction, so we will focus on the diffraction. I have to say some words also about neutrons, because it's also very powerful technique, and the diffraction of neutrons really important for us. So, few phrases about neutron. You know that it's electrically neutral particle with a mass close to the mass of proton. It's not stable in free state. The half-life period is about 10 minutes. And the most important feature of the neutron that it has a magnetic moment. So it's a bit, it can be a bit tricky why the electrically neutral particle has a magnetic moment, but we have to recall its intrinsic structure. It consists of 3 quarks and 1 up, 2 down, and they have some electric charge. So this is the origin of the magnetic moment. And this is important because using neutron diffraction, we can also read not only the crystal structure, but also magnetic structure of the material. So we'll talk a bit about the neutrons and how to produce neutrons, how to generate. We can use some kind of isotopes, unstable elements, which decay and produce neutrons. We can use particle accelerators, and we can use some light elements as targets and bombardier them with some particles, and also it's possible to produce neutrons. Or we can use research reactors, which is more often way for scientific purposes, of course, the more often way to produce neutrons. And there are several types, at least, of the research reactors. On this slide, I guess you can see the first type of the fission reaction, so-called. So then the neutron is absorbed by uranium nucleus, and it becomes to be isotope, which is not stable, and it will split and emits, release several neutrons. In this reaction, 3 neutrons. And there is a list of scientific centers where this type of emission of neutrons is used. In LL, in the Centrum, in France also, in Germany also, and in the United States, the most powerful one. I mean, we can compare the energy of the reaction. So the next type of the way how to produce is spallation, so-called spallation sources. So then the accelerated proton collide with the particle, and as a result of this interaction, we have a release of neutrons. So this type of emission is used also in Europe, in PSI, Paul Schroer Institute in Switzerland, in ISIS in Great Britain, and also in United States. And the second type of this reactor is so-called fusion. When we have a fusion process. Yeah. Then light elements fuse together. Light means hydrogen and isotope of hydrogens. And as a result of this fusion, we have a release of neutrons. Also, some scientific centers which use this type of production of neutrons. So this is just information how we can get these neutrons and the list of the facilities around the world. They are clickable, I mean the links, but probably later I can upload this presentation, and if someone interested in this, we can find these particular centers and estimate if it's really interesting for you. So I will talk a bit about this German center in Berlin, Helmholtz Center in Berlin. It has neutron head, actually. Neutron reactor, okay, at least it exists, and also synchrotron. There are two campuses in Berlin. And I made really a lot of experiments for diffraction in this centrum. Unfortunately for me, now it's not more in operation from the beginning of this year. For some reasons, political, ecological, I don't know exactly. It was shut down this January. So for me, it's a disaster. But it's like a kind, I would say, it's kind of tribute, my tribute to the centrum, because I made, I don't know, 100 experiments there. So, and I have to say a few words at least about the instrument and the reactor there. So this is the scheme of the reactor, the reactor core, and around the reactor in the experimental hall we have the instruments, and here we have so-called hot neutrons. Hot means high energy in the experimental hall, and in neutron guide hall we have cold neutrons, and also instrument which needs lower energy, lower as compared to experimental hall. Neutrons, say for small angle, I guess, where is it, instrument which I used to before, SANS, small angle neutron scattering, it needs lower energy. And for diffraction, we have to get high energy neutrons. So the instrument, say E9, FirePort, its abbreviation, the most interesting instrument for me. So I will say a few words about this instrument. FirePort, its abbreviation from fine resolution powder diffractometer. And basically the principle, it's understandable. Yeah, we have a reactor which produce neutrons. They go via the guideline and they collide with the sample. Sample is mounted somewhere here. This is cryostat, and the guy who is trying to hold it, it's also me on the background. And this black big device is a detector. It's a really fast detector, so it's convenient to make experiment there. Was convenient because we can quite easily get good statistic, diffraction statistic in a few hours. We can get really nice spectrum. So this slide we can see some parameters, technical parameters of the instrument and the flux and the resolution. And of course, it's very important to plan experiments, to know the parameters of the detector, of the instrument. Okay, so what kind of information we can get from this type of experiment, diffraction? We can estimate the phase of the material, what in reality we have. We can estimate the symmetry of the material. Symmetry means space group, means unit cell parameters, means ions, occupation of the ions, their positions, and knowing these parameters, we can calculate the distance between the ions, the angle, which is really important to describe properties of the material. So if we know the structure, it's possible to say what or predict the properties of the material. So few formulas, but they are quite important. We have to know intensity of scattering, and the intensity is a parameter which says about the value of interaction between the incident radiation and the matter. And one of the important parameters here is a cross-section, sigma. This is characteristic parameter, and it's tabulated, so we can find it in the tables. And the double differential cross-section, the formula is written here. It has two components, and to get diffraction, we have to take care about the coherent part of this this equation. Coherent. Coherent means the momentum is conserved during this interaction, and not only coherent part. Okay, because we have coherent part of interaction and incoherent. It's also useful for other kind of experiments. And talking about coherent scattering, yeah, interaction, for diffraction, we need only elastic part of this coherent. Inelastic also important to get phonon spectrum and for other information, but to get structural information, we have to consider only elastic part of this interaction. So about this cross-section sigma, this is tabulated parameter, and for X-ray radiation is quite trivial dependence between the scattering amplitude and the atomic number of the element. For X-ray, it's just linear dependence. The heavy element we have, the heavy, yeah, the more intense scattering of X-ray radiation we have. So that's one of the main drawbacks of X-ray radiation. We cannot precisely estimate the position of light elements like hydrogen, helium, even oxygen. It's not easy to refine the structure when we have these light elements inside in the crystal structure. But for heavy elements, it works fine. This is for X-rays. But for neutrons, this parameter cross-section, it's the dependence versus atomic number. It's really tricky. It can be even negative, so it's probably not easy to understand and to explain how it's possible, because cross-section is a matter, it reflects the value of interaction. Okay, but it's just information. So for neutron scattering, this parameter even can be negative, and it's there is no any function to describe. I mean, scattering intensity versus atomic number. So about the diffraction and about the scattering, I've already said about elastic scattering, and for elastic scattering, the K vector or wave vector K is conserved in this interaction. I mean, scattering. The K incident and k wave vector scattered. The modulus of them are the same. In the case of inelastic scattering, it's not conserved, the kinetic energy, so it's not the case for diffraction. This is just the image. So a few more formulas. So for X-ray, we already know that the magnitude or the value of scattering is a linear function of the atomic number. For neutron, it's not the case. And for neutrons, this structure factor, so-called, can be divided, or we can distinguish so-called nuclear scattering and magnetic scattering. Nuclear scattering, it's because of interaction of the neutrons and the nuclei of the elements of the matter. And the magnetic scattering comes from the interaction of the magnetic moment of neutron and the magnetic uncompensated, of course, magnetic moment of the electronic cloud of material. Yeah, so we have two components. This is really important because we can read information about the magnetic structure. So about the diffraction, coming back to the secondary school, we can write the diffraction condition like 2d sinus theta is equal to m lambda. Everyone knows what is d, it's the distance between the planes or between the nodes, the angle and the wavelength. In reciprocal space, the diffraction condition looks in a bit different way, but it's the idea the same. K vector, which is the difference between incident and scattered, is equal to G parameter of lattice in reciprocal space, G. And the Ewald sphere, which is an imaginary interpretation of diffraction in reciprocal space, but it's really important. I mean, this representation of these parameters of the unit cell in reciprocal space. Okay, so few words about the Rietveld method. What is the main idea? Okay, we have, say, diffraction regardless the origin of the radiation, X-ray, neutrons, or electron. So we have some reflections, yeah, because of the interaction between the radiation and the material. If it has crystal structure, periodically we have these maximums, yeah. And the idea of Rietveld method is to minimize the observed spectrum and its simulation. So we have to refine this crystal structure. We have to say software some initial parameters, and this software will try to adjust these structural parameters to minimize this function, the difference. And we can say about some reliability factors or R factors, which can be used to estimate the quality of this refinement. There are several R factors. Let's talk about this software, which can be used to refine the crystal structure. Actually, there are a lot, proprietary or free. I prefer to use called FullProf. It was written by Rodriguez, I guess. He still works, this scientist in ELL, Institute of Lowell and Given in France. And it's free software. It's good for me, and it's able to refine crystal structure and magnetic structure. Actually, it's not just a program, it's a set or package, and you can download it from this using this link. And it's a set of programs, so you can, at the first step, you can estimate the symmetry, then you can estimate the parameters, then you can estimate the ionic coordinates. So it's really powerful software, and it's free. So how it works? Let's consider as an example cobaltite system, lanthanum substituted by barium ions. This is complex oxide, and we know that the initial lanthanum cobaltite, it has rhombohedral structure. You can see the sketch of this unit cell on the slide. This is quite big, big as compared to perovskite cell. A big unit cell, the parameters are 5 angstroms, and AB is equal for rhombohedral lattice. C is about 13. So we have 6 primitive cells. Primitive, I mean perovskite cells inside this big unit cell, and we know how it changed the crystal structure and the properties of this material as a function of chemical doping with barium ions. So let's consider the most trivial case. Then the material becomes to be cubic. As an example, it's enough. So here we can see the diffraction pattern obtained by conventional X-rays in the lab. It's nothing special. This is cubic structure. The red dots are experimental information, and the black line, solid line, this is simulation of the spectrum. The ticks under the spectrum, this is Bragg positions, and the blue line is the difference between the calculated and the observed pattern. So this is X-ray from the conventional laboratory diffractometer. This spectrum is the neutron diffraction. I'd like to say why we have 2 rows of the ticks. One because of crystal structure, the second one is because of magnetic scattering. And so you see the difference. It's the same material, yeah. And the next figure is the diffraction pattern obtained by synchrotron radiation. The same material, 3 different spectra we have. So why we have 3 different spectra? Because, okay, the first reason, the wavelength is different. This is for X-ray diffractometer with copper anode. This is neutron diffraction with a bit different wavelengths. And this is synchrotron radiation with really small wavelengths. So the position of the reflections are shifted, yeah, and we can distinguish the same reflections located at the different 2 theta. Let's consider what we have here. We talk about this compound, it's solid solution, 50% of barium, 50% of lanthanum. It has, as I said, cubic structure. This base group is PM-3m. The unit cell parameter is close to 4 angstrom. The coordinates of the ions are fixed because it's cubic, so it's quite easy to refine it. Yeah, the only parameter we can refine is the parameter. Yeah, I mean unit cell parameter A, because A is equal to B and equal to C in the case of cubic structure. So let's see what happens if we get neutron diffraction spectrum at different temperatures. At room temperature, okay, we have some nice pattern. At low temperature, the same compound, and we have some extra reflections. The origin of this reflection is magnetic scattering. The crystal structure remains the same in this temperature range from 2K to room temperature. The crystal structure is the same, but we have a contribution of from magnetic structure because of magnetic scattering. We have neutrons, yeah. And on the right image, you can see enlarged part of the specific reflection, which where we have a contribution from nuclear scattering and from magnetic scattering. So sometimes it's not easy to distinguish the ratio between these contributions. That's why we have to make several measurements at different temperatures. Okay, I have made or reconstructed these patterns in d space, d distance in angstroms. This is spectrum obtained by neutron diffraction at 2K, and this is from synchrotron diffraction at low temperature. It's not really a big difference in terms of crystal structure. And you can see that some specific reflections, say the biggest one, which is the biggest reflection at this synchrotron spectrum, the d space is 2.8, I don't know, angstrom. And here for neutron diffraction, it's really small intensity, but other reflections are bigger. So as I already tried to explain, this is because of different scattering and different cross-section parameter, because here we have neutrons, one type of interaction, here we have X-rays, electromagnetic waves, and it interact in few words. The X-rays interact with the electronic cloud of the ion, and neutrons interact with the nucleus of the material. So this is principally different type of interaction. And we can see this enlarged part, yeah, the same reflection. And here we can even resolve the reflection. We can distinguish that it's in reality it's split using synchrotron radiation. And with neutrons, we cannot see the splitting because of the resolution of the instrument. So I guess on the next slide, we'll see this splitting of the, and we were lucky to have possibility to make two types of experiment, X-ray diffraction and neutron diffraction. So this kind of complementary techniques. With neutrons, we clarified magnetic structure. With synchrotron, we clarified crystal structure, and we got this splitting. Means we have two phases, two structural phases. Okay, this is not about the diffraction. It's just to explain that each method has some advantages and disadvantages. And it's really nice if we can make both experiments there. So about this phase separation, we discovered using synchrotron radiation. Okay, this is not because of, the phase separation. Then we refine two structural phases. It's not because of the drawbacks of the synthesis method. It's just intrinsic state of the compound, because then we heat it up. We found that it becomes to be single phase at elevated temperature, and at low temperature it's separated into the two different crystal phases and some parameters for these phases. And we were able to ascribe one structural phase to ferromagnetic phase and another structural phase to antiferromagnetic. So this is important to understand the nature of the magnetic properties. Why we have two components magnetically? Why we have two magnetic structure? Because actually we have two crystal structure, two crystal faces. So just the simulation. I guess I have still a few minutes. I have made a simulation of the diffraction spectrum for X-ray with this copper wavelengths, copper anode. Neutrons also with similar wavelengths and synchrotron radiation. Synchrotron and X-rays. Okay, actually synchrotron also has an energy of X-ray. They look similar, more or less, and for neutrons we have different intensity. The positions of the reflections are at the same, yeah. So the position, because we have the same compound and we have the same wavelengths, you see, yeah. But the intensity is different, as I said before, because of different type of interaction for neutrons and for X-ray with the matter. So in this software, just few slides to show how it works, the FullProf. We have to, I talk about refinement, not estimation of the crystal structure, but refinement. So it means that we principally know the crystal structure, but we'd like to know precisely the unit cell parameters, the coordinates. And to get this information, we have to say, software, okay, let's refine the spectrum using the space group, EBM. Let's put ions and the coordinates, and the software will adjust a bit to optimize, to minimize this function, delta function, to to minimize the difference between the calculated and observed spectrum. And also we refine the unit cell parameters. So this information is written like just text file, and using any editor you can change it, or you can also use some editor, but I prefer to do it by my hands. It's easy to control. So in this information we sorry, we put the unit cell parameters, the space group, the ions, the coordinates, and the software just refine these parameters. So, and for magnetic structure, we also can put ions, which are responsible for magnetic structure. In this case of material, it can be iron or cobalt, which are magnetically active. And we also can refine the magnetic moment ascribed to this particular ion and the direction of magnetic moment. So this information is in the file, which we have to construct to refine the crystal and magnetic structure. I guess I have to finish my presentation. I deleted some slides just not to annoy the audience. So I guess it's enough, and I'd like to thank you for your attention, and we'll be glad to answer some questions if people have any. Thank you.
Thank you very much, Dmitry. Very interesting talk, and thank you for showing us the different types of information you can get from using different radiation. Obviously, the floor is now open for questions. The way to do this is to use the raise hand icon in the participant list. So please, if there are any questions, please can you raise your hands? At the moment, I don't see any hands. Okay. I cannot believe this is true.
Everything is understandable, or
nobody knows how to use that raise hand icon.
Yeah, I don't know if this function is working or not.
Sorry?
Maybe we switch something. Maybe
Igor, you can try to write the hand.
Ah, it's appear. Yes, it's appear. It's working.
Yeah, one question I guess we have.
Here. Pushib, Raj, please.
I have some queries to slide 2 or 3 starting slides. Please come.
Yeah. About the electromagnetic radiation.
No, sir. Next one and next.
About the tube.
No, next. Where electromagnetism north poles are there. Yes.
This one.
No. After one. Yes. This one.
Okay.
This one. Please explain one times more that that Wigner top views and Wigner top views. Can you explain one times more? I'm not getting this.
How it works, Wigler.
Yes, so Wigner.
Okay, so we have this storage ring, and when we put Wigler, then the electron is trapped inside this device. It starts to deviate from its initial trajectory. So it has additional acceleration. Additional acceleration means additional component of emission, of X-ray emission. And because the geometry of Wigler, sorry, this emission still has solid spectrum. In the case of undulator, we have interference. And these phonons interact between each other, and we have interference, and we have discrete spectrum of this emission. For Wigler, we still have solid spectrum, and the main idea just to get new component of emission. New because we have additional acceleration. First, we have acceleration because of bending magnets, and next we have this perpendicular to the initial trajectory acceleration because of permanent magnet. Yeah, it interacts with the charged particle. So we get this additional component of the acceleration and additional component of the emission spectrum. So it will increase the intensity of the emission. This is an idea to increase intensity.
Oh, thank you, sir.
Okay.
Okay, thanks. Are there any more questions?
This is basic, probably, information, and people know everything about this.
Okay, so, well...
Hello, I have a question. What is possible? You listen me?
Yeah,
yes. Dmitry, some about Rietveld analysis. It is some computational optimization on some model with experimental data.
Yeah.
Connect. So, but first it's necessary to create this model from which they can take this initial data for modeling, so compare with experimental.
Yeah, this is only one part of the software set. As I said, there is a package, and there are some instruments which can be useful to get information about this symmetry, initial steps, to make initial steps. I explained the next steps when we already know the model of the crystal structure, and we try to refine it. So we have to, say, inform software what model we'd like to use. So for this, we have to put, actually we have to put all the structural information. But this is the final step to refine the crystal structure. The idea to refine, not to estimate, not to clarify it, just to refine. It means we already know the model, just to refine it. But this is, again, this is the final step.
Yes, so first it is from basic theoretical crystallographic theory, construct this initial model, and you refine your experimental data.
Yeah, you can say like this. But in software, it's also possible to estimate the most probable models.
Yes, yes, for different crystallographic group, symmetric group.
Yes, exactly.
Yes, it is many much theoretical data.
Yeah, you have to put the information about the chemical element, the unit cell volume, and the pattern, diffraction pattern, and the software will try to estimate what are the most probable models, the symmetries, which can be.
Yes. Okay, good. Thank you very much.
Okay, thank you very much.
So,
Are there any more questions?
another, I guess, raised hand.
Yeah, good morning, sir.
Morning.
I have a small question.
Not really good quality.
Sir, can you hear me?
Yes.
Not very well. Can you go closer to the microphone?
Or speak louder a bit.
Okay. Sir, I have a very small question. So, in your presentation, I have seen SPR diffraction spectrum and neutron diffraction spectrum at low temperatures, right?
I'm sorry, I don't think we are hearing you. Can you speak louder?
Can you hear me now?
Yes, that's better.
Yeah.
Is it okay now? Could you please wait for a moment? I just change this. Hello?
Hello, please.
Yeah, yes, sir. So my question is, can SPR and X-ray diffraction pattern will be same at room temperatures or will they differ?
I'm not sure I got the. Probably Duncan can.
Unfortunately, I didn't either. So
Probably we can. Probably.
Can you repeat again?
Or it's possible to write it. I don't know.
Sir, from your presentation, what I see is you mentioned neutron diffraction pattern spectra and SPF spectra at low temperatures. Hello?
I'm sorry, it's impossible. I don't think we can hear you.
Too low quality.
Okay.
Okay, probably.
Okay, sir, I will type the question. You can see.
Okay, actually, I'm available via any messengers or email address, and we can ask me directly if some questions left.
Okay. Well, I think we can thank the speaker again.